Again, I come back to the idea that basically there's really only two ideas: substitution and by parts. Trig integrals, really we're talking substitution, but we're going to substitute trig to solve it and things like that. So let's have a look and build it. We have our standard integrals, of course. So we know sine goes to negative cos, cos goes to sine, sec squared goes to tan, tan eventually can go to the log of sec or minus the log of cos, whatever you prefer. So they're our basic ones. Well, let's now look at, first of all, sine to the power, or cosine to the power, of course. Essentially the same answer, but remember cosine gives you the negative, the complement. So we'll just look at sine. Whatever technique we use for sine, we can use for cosine as well. Well, sine to the power of 1 is our standard integral, so it's minus cos. Make the power 2. Sine squared, we know now we use our double angle result, change it to a half of 1 minus cos 2x, and we can integrate that. Okay, let's raise the power. Sine cubed. What do I do for sine cubed? What I do is I split it into two things. I want to create derivative times function. Now, yeah, sine x is not the derivative of sine x, but cos x is, and I can rewrite sine squared as 1 minus cos squared. And I have now derivative times function, sine being the derivative of cosine. If you don't see it, there's my substitution. U equals cos x, so du becomes minus sine x dx, sub in, and we have our answer. And in fact, whenever the power is odd, we can always do that. Factorize out the power of 1, then the other one will become an even power. Well, the even power we can always write as, in this case, sine squared to some power. And then the sine squared I can always change to 1 minus cos squared. Then I can do my substitution, u equals cos x, and go from there. So that's the technique I'll always use on an odd power. Pull out power of 1, that's going to become my du. Sine to the power of 4 then, I don't do it that way. What I do now is say, well, if it's an even power, I can always write it as sine squared to the power of something. In this case, it's sine squared squared. The sine squared, I now use my double angle result. And it becomes a half, but I'm squaring it, a quarter. 1 minus cos 2x, but now that's all squared. Then I can expand that out and deal with each bit individually. So I've got 1, well that's nice, cos, and then the cos squared, I'm going to have to use the double angle result again. But now I've got something I can integrate completely. And there's our answer. So whenever it's an even power, factorize it as sine squared to some power, and then use your double angle result. And you might have to use another technique depending on how high the power is. Okay, and here's odd, just to take it further. Odd power, pull the sine x out. I can write that now as sine squared squared. Sine squared is 1 minus cos squared. I can now do my substitution, u equals cos x, and eventually we get the answer. And I don't think I bothered with sine to the 6, but that pattern we could keep going with. Okay, that was if it was just sine to the power of something or cos to the power of something. Well, what if we got a combination of both? Generally we're going to do these by a substitution, either u equals sine x or u equals cos x. Here's one. Cos to the power of 5 sine cubed. I'm going to rewrite the sine cubed. I'm going to pull out the sine to the power of 1. So it's the same idea. I pull out to the power of 1. Now in this case, I could have pulled out the cos, because whatever I'm left with then goes to an even power. Then I do, in this case, 1 minus cos squared. If I'd done the cos, I could have pulled the cos x out. I would have been left with cos to the power of 4, which I could have written as cos squared squared, and the cos squared I could have written as 1 minus sine squared. Let's substitute in, and we get it. Let's say, if both are odd, I can choose either of them to pull out. But I will choose usually the higher power to stay as it is, because it's going to be less work. So the lower power, that's where I'll pull the du out of, if you like. So in this case, cube was the lower power, I pulled the sine out, rather than going with the cosine. One's even, one's odd. Okay, in this case, I'm going to pull out the cos x. Pulling out the cos x, I'm left with even powers. The sine's already to the even, so I leave that alone. That's why I didn't touch that one. but the cos is to the odd. Pull the cos out. That now leaves me with cos squared, which I can write as 1 minus sine squared, and I can do my substitution. U equals sine x, add 1 to the power over the power. There we go. So if one is odd, one is even, then the even's going to be the u. So in other words, the odd is the one I'm going to pull out to be the du. Both even then. Sine squared, cos squared. Well, I'll just change one of them to be the other. I've chosen the cos squared to make 1 minus sine squared. I could have chosen the sine squared to be a 1 minus cos squared, but now I only have one trig ratio in there, sine, and then I just deal with each individual bit. Sine squared, we know how to integrate that. Sine to the power of 4, well, we just saw a technique to integrate that as well. And I'm going to cheat and just write down the answers we've already found. So there were the answers we found before for sine squared and sine to the power of 4. Tidying it up, there's my answer. So if both powers are even, up to you which one you want to do. Again, I would change the lower power. In this case, they were both equal to 2, so it didn't really matter. But I would choose the lower power to be the one I change. That's sine and coses and combination of each. Let's look at tan. Again, cotan being the complementary ratio, be the same technique. Tan to the power of 1. Well, yeah, that's minus the log of cos or log of sec, whatever you prefer. Tan squared, I can rewrite as sec squared minus 1. Integrate sec squared and we get tan x. Okay. What about tan cubed? Tan cubed. I'm going to split. I always will take out tan squared, leaving me with tan. Okay? Because then I can break it into 2 integrals. One becomes tan x sec squared. So I have the sec squared, which is the derivative of tan. That's why I always pull out tan squared, because I can change it to sec squared minus 1. Sec squared is the derivative of tan. It then leaves me with another integral, in this case the tan of x, and I know the integral of tan to x. So substitute in, and we have it. Tan to the power of 4 then, it is no different with tan. I'll just pull out a tan squared, which I can change to sec squared minus 1. Change it into 2 integrals. I'll always get one where I've got derivative times function. In this case, the function is tan squared. And then I'll have another tan integral to do. Integral of tan squared. So I can do my substitution for the first one. Integral of tan squared we worked out before, so I've just subbed that straight in. And whoops, and we get our final answer. So tan's nicer because it's just the same technique every single time. Pull out tan squared, change it to sec squared minus 1, and then deal with the new integrals that arise. Sec or cosec, again cosec being the complementary ratio, so the same technique will be used. Sec, how on earth do we integrate sec? It's obvious when you think about it. Let's multiply top and bottom by sec plus tan. Of course it's not obvious, but now it is. Right? Why? Look what happens when you expand the top. I get sec squared plus sec tan, but sec squared is the derivative of tan, and sec tan is the derivative of sec. I have derivative on function, so it is the log of sec plus tan. Now that you know that, go straight from the integral of sec to the log of sec plus tan. That is the standard integral. Okay? And sure, if they asked us to prove it, we've got to go through that process. We just know sec integrates to give the log of sec plus tan. Sec squared, well, that's a standard integral, tan x. Sec cubed, sec cubed. Okay, well let's pull out sec squared. Can't really rewrite that as derivative times a function. So now I do it by parts. I've got 2 functions multiplied together. Do it by parts. I'll make u equal to sec x, and when I differentiate sec, I get sec tan. dv is sec squared, which I can integrate, and I get tan x. So uv minus the integral of v to u. Gosh, that would be nice if it was sec squared tan, but it's not. It's sec tan squared. So I change the tan squared to be sec squared minus 1, split it into 2 integrals. Integral of sec, I now know, it's the log of sec plus tan. Integral of sec cubed, that's what we're trying to find. I now read it like it's an equation, and I say, well, 2 times the integral of sec cubed is sec tan plus the log of sec plus tan. Divide both sides by 2, we have the answer. And that's the technique we use for odd powers of sec. We'll always do it by parts. That's why you keep your fingers crossed. If you're going to give me a sec one, please give me an even power. Please give me an even power. Just all your thoughts. Hope you get it. Because sec to 4, a lot easier, because I can write that as sec squared times, and it will be sec to an even power, which I can change to 1 plus tan squared, and that I can do with a simple substitution. So the even powers are really nice with sec. The odd ones are like horrible. Well, not horrible, but more work. Add 1 to the power over the power. There we are. So even power, pull out your sec squared. That'll leave you with sec squared to some power. Use 1 plus tan squared and you'll get there. So that's 4G.